Okay, the last thing we're going to talk about with radioactivity is an application. Radioisotopic dating. How we can use the predictable decay of radioactive isotopes to determine how old something is. So you've probably heard of carbon dating, using carbon-14 to determine the age of biological remains. And this works because of a natural process in the environment. Nitrogen-14 creates carbon-14. Right? This happens all the time in our environment, in our atmosphere. So carbon-14 ends up in plant material, ends up in animal materials constantly, and it's in the food cycle, and it's in the air we breathe. So as a living being, you are constantly taking in carbon-14, both through breathing and through any of your food supply. So you're constantly replenishing any carbon-14 that has decayed. So over time, your carbon-14 levels stay pretty regular, pretty constant, unless there's some kind of event that raises carbon-14 levels on a global scale. But when an organism dies, it no longer is taking in carbon-14. So all the carbon-14 levels just simply decay at the predictable rate based on half-life. So we can compare how much carbon-14 is in a living species compared to biological remains to figure out how many half-lives that carbon-14 has been through in the remains. Alright, and then carbon-14 breaks back down into carbon-nitrogen and the whole cycle starts again. So normally this ratio of carbon-12 to carbon-14 is used to determine the age of biological remains. So we're still going to use the integrated rate laws that we've talked about for first order, either with nuclide amounts or with activity. But we're rearranging the equation to solve for T, because this is what we're trying to figure out. We're trying to figure out age. So using the same integrated rate law, just rearranged to solve for T, we have T is equal to 1 over our rate constant K times the ln of our A naught over AT. And in this case, A naught is the activity of the living organism, so something that is currently alive, and AT is the biological remains. So in this equation, I like to think of it as the living over the dead. Alright, so that helps you remember which way to do this ratio. So we're going to use that equation, and we're going to solve for an age. Alright, we have a bone sample that has an activity of 4.98 disintegrations per minute per gram of carbon. This is just an activity unit. Don't let this bother you. If the carbon-12 to carbon-14 ratio for a living organism has a specific activity of 15.3 disintegrations per minute per gram carbon, how old is the bone? Alright, so we have the half-life of carbon-14, and we have our specific activities. Alright, so here's our equation. 1 over K times the ln A naught over AT is equal to the age of the bone. So if we look at our equation, we have our two specific activities, but we don't have K yet. That's what we're going to use this half-life information for. So remember, half-life is ln of 2 over K. So ln of 2 over K is equal to 5,730 years. So let's find K. Alright, so ln of 2 divided by 5,730 0.000121 over years. Alright, so there's our K value. So we're going to plug that in. Trying to find T. 1 over 0.000121 times the ln. Alright, remember this is living over the dead. Our living organism had a ratio of 15.3. Our biological remains was 4.98. Alright, so there's our relationship. So now everything on the right side of the equal sign is a real number. So we can figure this out. 1 divided by 0.000121. 8,264. Call that 0.5 times ln 15.3 divided by 4.98. 3.07. Alright, let's do the ln of that. 1.122. Alright, so then multiply it by 8,264 and a half. 9,276 years. Alright, and our units come from the fact that our K was in 1 over years. So this is the approximate age of the bone sample. Alright, last example with this, we're going to do with percentages. As you may have guessed, if you start to look at carbon-14 dating, there's a limit to how useful carbon-14 can be. After a certain age, there's not enough carbon-14 in a sample to get accurate results. So if something is very, very old, and normally carbon-14 has a limit of about 36,000 years, you have to go to a different isotope. Now it's the same principle even if it's not carbon-14. So potassium-40 is very often used to date things like fossils, rock samples, that might be much, much older, like millions of years. Potassium-40 decays into argon-40. So the half-life is 1.248 times 10 to the 9th years. Okay, so very long half-life, so we can use it to date very old things. How old is a rock sample that contains 25% of its original potassium-40 amount? Alright, so we're going to use the same equation we had before, solve for time, where we're looking at our living and dead ratios. But this time we're using percentages. So the first thing we're going to do is find our K by using our half-life information. Half-life is ln of 2 over K, which is 1.248 times 10 to the 9 years. Alright, so setting this up, we can then solve for K. So 5.554 times 10 to the 8. Alright. 1, 2, 3, 4, 5, 6, 8. Alright, so this is our K value. We're going to plug that in over here. 1 over 5.554 times 10 to the 8 times ln. Alright, so here's where we have to think about our percentages. So our living percentage is going to be 100%. Okay, living is kind of a relative term here. We're talking about rock samples, but we're talking about modern or contemporary that keeps getting replenished. Our dead sample is 25% of that. Alright, so we're going to put that on the bottom. So now we can solve. Everything on the right side is a real number. So 1 divided by 5.554 times 10 to the 8th times ln of 100 divided by 25. So it looks like 2 times 10 to the 9 years. Another way to do this one is going back to our other calculation where we had nt is equal to no times 1/2 to the n. So if you remember that equation, we have 25% left. We started with 100 times 1/2 to the n. Now in this case, we're trying to figure out n. Alright, so if we do this calculation, we're going to take 25 divided by 100. Alright, that gives us 0.25 is equal to 1/2 to the n power. And how do we find n then? Log of 0.25 over log of 1/2 is equal to n. So we can solve this. Log of 0.25 divided by log of 1/2 gives us 2. So n is 2. It's been through 2 half-lives, because if we start with 100%, one half-life is 50%, second half-life is 25%. That's what we're at. So we've been through 2 half-lives. So we can use that based on the years here. So we had total years over half-life. We've been through 2 of those, so just multiplying by 2 from our amount we had, 1.248 times 10 to the 9th times 2 is our 2.5 times 10 to the years, which is very close to what we had over here. I think our calculator cut us off.